Okay, so it turns out I am a hoarder. There, I admit it. I have lots and lots of blue pens and red pens and green pens and black pens. Now, turns out half of my pens are blue, half of my a quarter of my pens are black, and 15% of my pens are red, and 10% of my pens are green. I have an infinite number of blue pens and an infinite number of black pens, and an infinite number of red pens and an infinite number of green pens. They're all over the place, but they exist in these proportions. Does that make sense? Okay, so suppose that I'm running to class, and so I pick, say, 10 pens at random. What's the probability that, the number of blue pens is 5, the number of black pens is 2, and that I get exactly 2 red ones and exactly 1 green? Okay? Is that okay? Yeah. Well, let's think about this. Okay, so I've got 10 pens, right? I'm going to do 10 trials. 3, 4, 5, 6, 7, 8, 9, 10 trials. Now, the chance that I get what's the chance that I get 5 blues and then 2 blacks and then 2 reds and then 1 green? Well, that's not too hard to figure out. That's just going to be the chance of getting a blue pen raised to the 5th power, right? And then the chance of getting a black pen, which is 25%, raised to the 2th. And then the chance of getting a red pen, which is 15%, also raised to the 2th. I'm getting two of those, right? I want to know the chance that I get 2 of those. And then times the chance that I get a green pen, 10%, raised to the 1th. And this is by independence, I think, right? By independence. But now I haven't accounted for the order in which this occurs, right? I could put these blue pens anywhere, right? Well, almost anywhere. Yeah. Maybe I gotta pick 5 places to put those blue pens. And then once I've done that, which, by the way, how many ways can you place those 5 things? Well, there are 10 places total, 10 trials, and then I've got to pick 5 of those 10 trials to result in blue pens. And then I've got some number of black pens. I'm saying let's get 2 black pens. There are, let's see, 10 minus 5 choose 2 ways to place those black pens once I've placed all the blue pens, right? Because there are only 1, 2, 3, 4, 5 spaces remaining to place the black pens, right? Okay, maybe I'll even write this part in black, like that. And then for the red pens, once I've placed the blue and black pens, there are, let's see, 10 total minus the 5 blue minus the 2 black, and then choose 2, right? There are 2 ways. Let's see. I need to know how many places out of these remaining slots, these 1, 2, 3 places, to place the red pens, right? How many ways can I place the 2 red pens there? Okay. So now once that's done, I'm only left with 1 way, right? Or 10 minus 5 minus 2 minus 2. Choose 1, right? Place to put that remaining green pen. Okay. Now let's rewrite this a little differently here. Let's say this is going to be, so it's 0.5 to the 5th times a quarter to the 2th times 15% to the 2th times 0.1 to the 1 times, I'm going to write this out the long way. That'd be okay? If I put say 10 factorial over 5 factorial 5 factorial, and then times, let's see, what's 10 minus 5? That's 5, right? 5 factorial over 2 factorial. 3 factorial is what this one is. And then I've got 10 minus 5 is 2. 10 minus 5 is 5. Minus 2 is 3. So that's 3 factorial over 2 factorial, 1 factorial, right? And then the green stuff becomes, let's see, 10 minus, this is 1 factorial over, whoops, this is 1 factorial over 1 factorial, 0 factorial, right? Now check this out. You got 5 factorial cancels 5 factorial, and the 3 factorial cancels with the 3 factorial, and the 1 factorial cancels with the 1 factorial, and of course this goes away, and there is the phone. Let's see, so this becomes 0.5 to the 5th times 1/4 to the 2th times 0.15 to the 2th times 0.1 to the 1 times, what is this? Looks like 10 factorial over 5 factorial, 2 factorial, 2 factorial, 1 factorial, right? Yeah. Okay, so that's that probability. And I think it's not too difficult to see that all this basically generalizes. You know, suppose that you have, in general, suppose you perform in independent and identically distributed trials where each trial results in outcome K with probability. There's the other phone. Probability P sub K. Now, let's let X sub K denote the number of observations of type K that you observe when you do these in trials. Then the probability that x1 is, say, that much, little x1, and x2 is, say, little x2, and so forth and so on, up to, let's say, you know, you've got, I don't know, let's say you have K types. There are K types. This turns out to be n factorial, total number of trials, over x1 factorial, x2 factorial, xk factorial, times p1 to the x1 times p2 to the x2 times pk to the xk. Okay? Yeah. This is called the multinomial distribution. That is, when you're looking at the joint distribution of x1 and x2 all the way up to x whatever, the joint distribution of these random variables is the multinomial distribution. Notice that it reduces to the binomial distribution. If k equals 2, then you have n factorial here, x1 factorial. In fact, let's just do that. If k equals 2, then, you know, what do you have? You know, this is the chance that x1 equals x1 and x2 equals little x2. But hey, you know what? if you only have two types of items, then this is sort of redundant, isn't it? This is just the probability that x1 equals x1, because you know the rest of them have to be of type 2, right? And so then this will be n factorial over x1 factorial, right, times x2 factorial times p1 to the x1 times p2 to the x2. But, of course, here x2 is n minus x1, so this really is n choose x1 times p1 to the x1. Let's see. P2, though, if there are only two possible outcomes for each trial, then P2 is 1 minus P1, right? Raise that to the x2. Yeah. So the multinomial just generalizes the binomial. That is, if you're looking at performing n identically distributed and independent trials where each trial results in one of, say, one of k different outcomes.